Get started here. So welcome everybody to our webinar on satellite environments testing with a special focus on some of the exciting things going around UNSAM and the South American space industry. So thank you for joining us. And then just as a courtesy, the webinar here is being recorded today. So anybody who can't attend will be able to receive a copy of this later to review. But why are we here today? There's new lowered barriers to entry and ways to compete now available to the South American space industry, made possible through some cutting-edge innovations provided by both academic as well as industry partners to design, manufacture, and test and launch satellites successfully into space. Satellites are part of our everyday lives, whether we know it or not. Just this morning, I was using my cell phone, using the weather app. I'm in upstate New York at the moment, and we almost got hit by a tornado. And if it wasn't for the satellite technology behind that, I wouldn't have known about the risk. So with that being said, this event is designed for students, engineers, anyone in academia or industry who's eager to learn about some of the latest advancements in environmental testing, specifically for satellites and related spacecraft and components. Real quick, I just wanted to give a short and sweet overview of who we are. Our company is MSIDFAT. That's Maryland Sound International Direct Field Acoustic Test. We're specialists in acoustic testing for the space industry. And as the trusted partner in acoustic testing, we've tested over 200 spacecraft and satellites for launch certification. Today's webinar, we're going to cover a wide range of topics. Our presenters today are Dr. Gabriel Sanca from UNSAM. He's going to give an overview of the university and its engineering programs, as well as the exciting news and the vision for its LabOSat, newest spin-off venture, and some of the capabilities of these state-of-the-art facilities for small satellite and spacecraft testing. Also, we're joined by Dr. Alex Carella, who's going to talk about new proven methods for satellite launch certification that can help lower the barrier to entry. He'll give an overview and an introduction of direct field acoustic testing, some of the differences between direct field versus reverberant chamber acoustic testing, which is a traditional method of having conducting acoustic qualification for satellites, and some of the economic and technical advantage of the direct field acoustic testing method. And then finally, we have Chris Sensor coming online from Siemens Digital Industries to be talking about how we can ensure mission critical spacecraft testing and spacecraft performance through experimental testing approaches. And then we'll end the webinar today with some questions and answers. There should be a chat function. Please feel free to engage us as we go along in the webinar today. You can drop your questions in the chat and we will try to address all of them. If there's any question that we can't answer, we'll be sure to follow up with you after the webinar with an answer to your question. So let's dive in to the webinar. And I'm going to play a short video here. You can see a rocket launch and the environment that this goes through. So yeah, we can see the typical environment of a rocket launch and some of the violent or harsh environments that both the spacecraft and anything that it's carrying get into. And just to give some idea here, we know sound is energy, and that energy can be experienced as upwards of 145 decibels within the fairing, upwards of 200 plus decibels external energy. There's all sorts of events that surround this spacecraft too, from the takeoff environment to the reflected jet engine noise to even leaving the atmosphere and more recently re-entering the atmosphere environments. So what we learn is that precision, safety, and integrity of the spacecraft and the satellites is of paramount importance. And there's a lot of different loads that can get experienced in different ways that can impact the integrity of both the launch vehicle and the satellite. Acoustic testing is just one part of a test that a satellite might go through the overall series of qualifications and acceptance tests. Other ones include random or shine vibration, shaker table testing, electromagnetic interference testing, pyroshock, thermal vacuum chamber testing, and much more. So let's dive in and we'll explore with our experts more about these topics. First with Dr. Gabriel Sanca from UNSAM.
Well, thank you everyone to be here. First of all, thank you Bradley for making this possible, and all the organizations. Thank you to Alex Chu who will participate in this webinar too. I think it's a very good opportunity to us here and in UNSAM to share what the project we are involved and the project and the facilities we have in mind and the project we are having ongoing now too. I can switch from Spanish to English is necessary in some part of the presentation. No problem with that. I will start in English, and so everyone can understand and be in the same language. So I will be talking about the facilities project and some future ideas we have here at the University of San Martin. Great. The outline of my presentation is present here. I will start talking about UNSAM itself, the university, all the programs we have, centered in the engineering program that are related to the topic we are covering today. Then I will talk about LabOSat, that is our flagship project, and some ideas we got to the future. I will talk about LINE, not line. LINE is the name of our laboratory is in which I am now. I'm here. Is the Laboratorio de Integración Nanoelectrónica, the Nanoelectronics Integration Lab. The name is because of our background from the electronics. I will talk about that. Then I will talk about the environmental testing capabilities here at UNSAM. I will cover then the opportunity for collaborations, and I will finish with some conclusions and time for questions. If do you think, Bradley, now maybe we can go later with that at the end.
So, yeah, we have time for Q&A at the end.
Yes, great. Well, sorry, I will be drinking mate. This is better than water for me, so sorry for that. Well, first of all, this is South America. Yes, we will start with this idea. We have, I don't know if you see the cursor, but well, Argentina, Uruguay, Brazil, Chile, you know, Paraguay, Bolivia, Peru, Ecuador, Venezuela, all the South American continent. Those who are not from South America, maybe you are from the States and you are familiar because we are playing the Copa America right there, so you know about us. And in this red spot here with the arrow, we are there now. That's very close to Buenos Aires, where the university is located. The University of San Martin. This is a picture of our campus. It's called UNSAM. We are a younger university, 32 years old. We have several programs and different schools. I will talk in a minute about that. The university has a strong commitment with innovation and with technology and with research. And in the last years, it was really famous here in Argentina because several developments that were made here, like COVID vaccine and several developments related with that. We also have telecommunications, electronics, and space programs that I will tell you in a minute. So this is a Google Earth image of the campus. Here is all the campus. It's located very close to Buenos Aires city, to the capital city of Argentina. It's like attached. Here is Avenida General Paz. That is a very important avenue here, and divided what is the capital city of Argentina, Buenos Aires, with other cities that are in the surroundings of the capital. That is called the Great Buenos Aires area. So now I'm here in the red arrow, and I will be talking later about this blue arrow too, because we have the intention of put some part of the new facilities of the lab there. So our campus is here. The campus is like really good connected. You can here by car or by train very easily because we have here this Avenida General Paz by car, and also the train station that is pretty close to the campus. The campus itself has a reminiscence from the train. It was not only a train station in the past, but also a railway workshop. Here the trains were like repaired, and so we have this historic past, or we have this history of the trains here at the university. And if you walk through the campus, you will see different structures and buildings that were part of that train station or train workshop, like many years ago. And now it's like restored and put into value in this beautiful campus we have. So the university has 12 academic units divided into 8 schools and 4 institutions that are in collaboration with important institutions here. We are in what is called the technological area of Miguelete, in which not only is the campus of TEUNSAM, but also the National Institute of Technology, the INTI, and the National Nuclear Institution, the CNEA is called. So this is like a very important technological area. We have collaborations with this institution, national institution, very important, and we work in collaboration with them. We have programs, careers in which we develop in collaboration with this institution. So it's a very strategic point here in Argentina, and is near to Buenos Aires, in which we have these connections with these important research centers too. And we also have a secondary school, the high school, technical high school, and university teaching center at the San Martin Federal Prison, in which people that are private from their liberty can study, and it's a very important place for us. We have several programs in these schools. We are particularly in the School of Science and Technology, in which we develop the most of the not it's not the only school that have engineering, but we have the greatest amount of engineering programs. We have also our undergraduate courses, pre-undergraduate and graduate programs too, including 21 PhDs. We have one in our school from applied science and engineering. Just to have in mind some numbers of the university, as I said before, we are like a pretty new university compared to other universities, not only in the region but in the world. We have only 32 years old. We have more than 24,000 students. I think these numbers are, this is from the last year. Now we are close to 26,000 students, and more than 2,000 faculty members. So just to have an idea of the size of the university, as I said, it's a kind of new university here in Argentina. We have this pretty campus that is. We have many things, important things to say. Like we have all the careers here that is not very common in Argentina. So you can be walking through the campus and have the engineering students, but also maybe arts students, and then you have the social science student. We have all here in the same campus. That is not very common in Argentina. It's part of the strengths of the university. The school I mentioned before, the School of Science and Technology, is our school. We have 8 engineering careers, including space system engineering, including electronics engineering, which I'm also part. I'm the head of the program. And we have also telecommunications engineering. These 3 are like very related to the topics we are covering today. So I think it was really important to say it. We have also 3 bachelor's degree programs, 3 undergraduate courses, and 1 PhD program, as I said before. So as we are in the university, the human resources training is a key aspect for us, and we have that in mind in every project we develop. So I will talk now about this LabOSat, that stands for Laboratory and a Satellite. This was our first approach to the space science, or to the space projects. As I said before, we have our background from nanoelectronics, electronics in general, but particularly in nanoelectronics. Our group started working with nano devices and nanomaterials. And this full project started with the idea of characterizing electronic components and devices in orbit or in Earth's environment in general. In LabOSat, we think about or we used to think about, or we are more familiar to think about the space environment as from the point of view of ionization radiation. It's like we think about then the thermal and vacuum, and in the last we think about vibration, but we are like changing that mindset now. We are trying to be in all the path to go to the space. But at the beginning, we think of the space environment as from the point of view of the radiation. So we start thinking about several experiments in which we can increase the TRL of these devices and enable the use of nano devices and electronics in general for future missions. So that's what how LabOSat started. Is started as a collaboration of different institutions, and like I have universities and institutions here, including, of course, the University of San Martin. We design experiments to put on board of satellites. We develop scientific payloads for small satellites, and we, of course, as said before, train highly qualified human resources because we are in a university, and that's very, very important to us. So we started our journey to space more than 10 years ago from a very tiny piece of silicon. We developed there our own devices in lower scale at a clean room, for example. At the very beginning, we were studying one particular kind of devices that is called manristors, and we were thinking about them to use as non-volatile memories. That was like the beginning. And we tried to test in a relevant field, in a relevant experiment. So more than 10 years ago, we go and talk to Satellogic, that is a company here in Argentina that develops satellites. And we say, we have this, we want to try to test this in a satellite. They say, okay, please don't give us this tiny piece of silicon. Give us some electronics in some context, a board that we can communicate and we can download the data. So we started with that idea. We have this piece of silicon. We have to integrate that silicon into the package, and that package might be exposed to all the test before flight. We develop a payload capable to test these devices and other devices in a space, in a satellite, in a small satellite. And we have this experience of this payload nine times in 10 years. The last one was in January of 2020, and the mission finishes in January of this year. So this is like a very summarize of the project's life. And these were like the past projects, and now we are in developing new electronics. This board is like a new version of the previous payload that has been tested in satellites 9 times. The new idea is to have it in a PC 104 format to be to fit into a CubeSat, and the new idea is to have a motherboard and a daughter board in which you can put the experiments and make it easy to have different devices to be tested under to be like development under test. We also develop an onboard computer that we are thinking right now as a payload controller. So we can have several payloads being controlled with the same OBC, but it could be used as a primary OBC too. So that was a very summarized idea of the project, and I will talk about now of the laboratory and the facilities we are buying and installing right now. First of all, this is like a whole idea we have this full cycle. We have already experience on the design of the electronics, the design of the PCBs, on the fabrication and assembly in a low scale, just for prototype purposes. We have completed this full part of the circle, but we want to complete the whole idea. We are intending to have a flat sat just to test different subsystems and payloads. We have a brand new shaker and our thermo vacuum chamber, and we also have a clean room for the assembly. So we are trying to integrate this whole path in a single laboratory with the background of the idea of characterizing electronics for small satellites, and to test them and to integrate them and to have the whole idea from the design to be able to integrate a payload or a whole satellite or a small satellite to be integrated or to be launched. That's the vision. So regarding the chip-back system, this is the actual photograph the company sent to us. We are buying a Rydberg Vacuum Science 12 UC vacuum chamber. It's a small vacuum chamber. They sent us the picture and it's flying to Argentina in these days. The thermo vacuum chamber is suitable for small sats. You have the dimensions there, but the idea is that you can put up to a 12U CubeSat or something about that size. We have plus and minus 150 degrees to make the cycling temperature, vacuum's level of 8 to 10 minus 7 torr. It is equipped with the residual gas analyzer and temperature control quartz crystal microbalance to perform outgassing testing and in compliance with the NASA standards for the satellite. So this is part of which we are installing now in the lab. This chamber is not in UNSAM yet, but it will be in a couple of weeks, and we hope we can install in the next month and having functionality. We have also a shaker that is from EST Solutions, and we have vibration research controller. The payload, this equipment is already in UNSAM. We are waiting for the installation from the company, from the provider. They have to come here and install and make the equipment work. We can put payloads up to 500 kilograms, and we can feature seeing random shocks and shock response spectrum test. And also we have a head expander for the x-axis shaking that have the same whole pattern that the X and Y table. So is part of the facilities we are installing right now. We also have additional equipment that is complement with all these. We have a semi-automatic PCBA system from the first company that includes the pick and place and the soldering oven. We have the 30 square meter ISO 7 clean room in which we intend to do all the integration. We have the flat sat system, lots of characterization or electric characterization equipment. We have that oscilloscope, vector analyzers, current and voltage sources, all that stuff. We also have a ground station in the UHF and VHF bands for operating and communicating to satellite. This is a project that was in collaboration with the Technological University of Berlin, and we have one station here at campus in the roof of the building which I am now, and we also have another that is the same ground station located in Antarctica. So that's a really important facility for us. And we also have computer numerical control for mechanical fabrication, including milling machines, laser cutting machines, and lathes to develop different mechanical parts. This is not part of our laboratory, but will be held in the same building. So we will have these all facilities included in the same building. So the collaborations and some final conclusions. We are open to collaborate with both industry and academia. We think we have to be part not only the Argentine ecosystem, but the regional ecosystem. We know that there are several countries here in South America that will maybe need these kind of services and collaborations. In Uruguay, Chile, Brazil, also Bolivia. We are like very open to collaborate and be part of the projects that want to be working with us. And we think that not only Argentina, but all the regions of South America must be part of the global chain supply and be part of the global market of satellites and development and all that. So we are open and trying to contribute in that idea. So just as a conclusion, we have developed an electronic characterization laboratory for the satellite, which is called LabOSat, in which we could perform the test of degradation of devices on a satellite directly. We are open to have a collaborative space for the regional ecosystem, and we want to also have services for the industry. So please contact us for any questions and any kind of project we can carry out together. And thank you for your time, and open to questions maybe at the end, or also the emails here, and we can continue now. Bradley.
Thank you so much, Dr. Sanca, for the overview. Our next presenter is from MSI DFAT, Dr. Alex Corella. He'll be talking about direct field acoustic testing. It's an innovative method that can help lower the barrier to entry on previously or historically very expensive reverberant chamber acoustic testing. Alex?
Yes, I was muted. Hola, buenas tardes, buenos días. No sé qué hora es de allí. Es como acá. Buenas tardes. Thanks, Brett and Gabriel, for co-hosting these and organizing this. This is an interesting webinar or discussion to have. Direct field acoustics is, I have to say that Argentina is a pioneer, or I think the jargon, the real term is early adopters. I think of the whole world, INVAP was the first one to see the benefit and to acquire a capability back in 2010, I would say 11. I don't know if somebody from INVAP, they might correct me, but I think it's 2011. They purchased a DFAT system from MSI. They have a facility capability down in Bariloche, and so there's been a long path to where we are now, and I want to start from the end, and the end is that this works. That this way of doing an acoustic test works, as testified by the 200 and plus satellites flying happily, floating happily in space, after being tested with DFAT. So this is a little gallery. I kind of fit 210 also because most of them I couldn't take pictures. But these are some of the most notable programs, and you can recognize Orion. There is the Cree module. We've done a lot of satellites. So This works. Now, I could switch to the phone and show you where I am. I'm in my lab, in our lab here in Baltimore, doing some tests, and there is always, I think it's interesting how sometimes we lose focus on what we're doing and why we're doing it, and there is a lot of discussions on the acoustic field, and if there are any acousticians in the audience, or somebody that is a fervent, somebody that likes chamber, a supporter of chamber. Sure, there is some acoustic field differences and acoustic equation that might not be exactly the same. But the acoustic is only one part of these tests. Like any test we do in not all in the space industry, but whatever test, there is a means, so there is a scope of a test. So the test is only a means to an end. And for what concerns the acoustic test, in the end is excitation, structural excitation. So as a matter of fact, there are only 24 microphones measuring the field, and there are 300-400 accelerometers measuring. That tells you what is important. So at the end of the day, what it matters is how much the spacecraft vibrates. So there is a lot of structural engineers, analysts that look at the vibration of the spacecraft. Now, this has been done in the Apollo days, and the chambers were the standard. And then these new things started to be used. These new, I call it a business-driven technology. I mean, with the speakers, there is very little we can do different from the chamber. There's nothing that we did that the chambers couldn't do it. So chambers could excite. So this is really a technology, a methodology that came out to save a lot of money. Not little money, a lot of money. So this is building a chambers so if a lab wants to equip itself with a capability of acoustic testing going through a chamber, is a lot of millions. If you want to use a DFAT system, depending on the size, a little millions, maybe less, but it's not a lot of millions. One. Second, you could use it as a service in your facility without having to risk any damage. So yeah, this is a way of saving money more than doing something which was not possible. So there's been a long way of papers and science and data and comparison, but eventually we came to the conclusion that the two methods are now both accepted, both capable of qualifying spacecraft and components, and so there is what I can with a certain certainty say as a equivalence between the two. Now, the history, a little bit of history goes to put in context. It was 98 when JPL had a first spacecraft called QuickSat, and they could do in a chamber, but the idea was that I think the chamber was broken or there was an issue with the chamber. So repairing and waiting and going somewhere else. Somebody had that light going on in the head. It was like, oh, speakers, we're doing noise, we're making noise. Why don't we use speakers? Loudspeakers, that's what they do. And so they called what at the time was one of the biggest firm in the country for concert and audio engineering, which was MSI. And of course, the owner of MSI, a bit crazily, but fortunately for all of us, said, "Sure, why not? We have plenty of speakers here sitting in our inventory. Come and get a bunch and make some noise." And so that's how it started. There was a lot of, at the time to control it, there were not many ways of doing it. So there was the random control from a shaker, so one drive to all the speakers, and there was a lot of noise. But if you look at the different microphones, the difference were so high, there was unacceptably high, the difference. was a field which was not uniform. But then they led to more development. They went to MIMO. And so by 2023, there were 209 satellites qualified. Enter Siemens in Europe. At the same time, it was a bit, there was like 11 years, 12 years the shift. But in 2011, we started to do a test. At the time, I say we because at the time I was a Siemens. And so we went to Toulouse to the first test, putting some satellite on a sphere. In 2018, I think so. Somebody from Federico might have been at the conference in Hedza, XMET in 2018, and we had a panel where we started. I was chairing this panel with all these experts on the panel. It was Paul Larkin, there was Ali Kulaini, and we started to put on the table the need of having a handbook. So there was one in NASA from 2016, and so also Europe now we're working on a handbook. And then in 2019 we qualified the first satellite in Europe, in Italy, Thales Alenia Space Cosmos satellite. So there was a long path. This was something I gave it to a Siemens seminar, and since Siemens is also part of this webinar, I think it's right to put this timeline how we developed the control system. So I had the two PhD students. One of them was actually Argentinian, Mariano Alvarez, and he came to see. We started to work with INVAP, and then I left Siemens. Different things happened, but the point is that we developed a full control capability with the MIMO narrowband to drive the set of speakers. Just a quick sidetrack here on reverb chamber. Reverb, if you have a reverb chamber, there is no question. You use it. That's how acoustic test is done, and there is no question. Nobody can raise their hands like, oh, reverb chamber no good. Now there is a little caveat to the size of the chamber. A reverb chamber is as good as the size. So the bigger, the better. But other than that, it's just a lot of money to run it. The gas to fill it, the pipes, the vaporizer, the concrete. If you're in the business of reverb chambers, you're in the business of concrete. That's your main. There's a lot of concrete, the walls, the suspension, the floor. So it's a lot of money to build a chamber. Now, when it comes to the actual data, so these are independent papers that I found is available in the literature. They looked at these are fairly big chambers. So 1,000 cubic meter, 1,100, 1,300 cubic meter is a lot of is a big chamber. So these are two European chambers. And what they did in these studies, they put a bunch of microphone and they looked at the dispersion. So how different each microphone was from the average. And the result showed that there is, of course, a very poor uniformity in the lower frequency, and somehow in the higher frequency they get a bit fancy too, but not so much. But in the lower frequency, it is actually pretty bad in terms. Now, to give you an idea, a smaller chamber, so they did another studies, and another paper that is in Canada, and they looked at the smaller chamber, so 500 and 150. And in this case, instead of measuring, they went through more an empirical way of looking at things, and they're looking at a uniformity criterion based on the number of modes per octave. So the way a chamber works is by reflecting the sound waves coming from the source and creating a modal density so high that the field becomes uniform. So it doesn't matter where you put your microphone. So the field that, it can be described as a diffuse field. So there's like all the equations that come in the sinc squared function, and you have a theoretically, so it approximates a theoretical diffuse field. And one empirical way of looking at this is by having at least 20 modes in each octave. And if by this criterion, these chambers would be probably not usable up until 125 hertz or 63 hertz, depending on the size, because you don't get to have enough mode. So there is not enough mode, so uniformity will be very bad, and therefore the field won't be diffused. So and so the chambers are good at a higher frequency, mid frequency especially. So above 100 hertz, above 150 hertz, they work really good. But to give an idea, a DFAT test is plus or minus 3 dB all across the frequency range. So that is one. Now, does it make any difference? Now we can argue about that, but it is true that we control in narrowband and we do not suffer from the size of the chamber. These are, again, data. These are data measuring different tests with 24 microphones and different controllers, different setups, different times. And you can see in a chamber, so these are data measured in a chamber, none of these chamber, but you can see the trend, which is actually exactly the same. So if I would put all on the, this is plus or minus dB, if I would put all in absolute values, you would have exactly the same trend that you see here in this paper. So that's a nice way of showing, that there's a scientific method which can be reproduced. So I love that science is science, doesn't matter who does it. So chambers do have these low frequency region that, again, is not affecting or is not changing the way we do test or has been done in the past, but it's something to bear in mind. Now, there is a lot of pros and cons. You will have these slides, so you can read them. I think that the biggest pros for a chamber is that it's unquestioned, it works, and you can reach extremely high level. Physics prevent us to go above 150 dB before the current going through the coil would create a meltdown of the coil, and the physics doesn't allow us to go today to 150 dB. However, the pros of DFAT are economically way more viable than a chamber. The risk of transporting a satellite is just a binary thing. If anything goes wrong, mission is delayed, and you don't want to be there. So staying home, staying in your lab, and getting the test done in your lab is probably like a masterclass, priceless. So here there is there is a bunch of, when we work in the space industry, there is always a handbook or a standard or something to look up in order to do the test. And when it comes to direct field acoustic testing, there are a couple of books available today. However, just like phones and technology are evolving at rapid pace, direct field acoustic testing doesn't evolve that much. That quickly. But since 2016, when these were first released, it's a different ballgame. Totalmente different. So we have gone from a square to rectangular MIMO control. We have gone from not controlling of coherence and cross terms to creating a diffuse field. So things have changed greatly. When it comes to on the 9th of July, so it was like on Monday? No, Tuesday. Tuesday, I don't know if you watched, but I did watch the launch of Ariane 6. And finally is flying, so Europe has a new access to space. That's great. But before flying, they already had a user manual available, and is the first launcher, the first user manual that explicitly contains the word direct field acoustic testing. Now, I'm not sure what happens when you contact them. I have to try now that they're flying. So like, hey, I want to use a direct field acoustic test. What do you say? I'm not sure what they're going to say, but I'm gonna find out, and I will share. But the point is that this has been recognized by the launchers, and I guess that there will be some work to be done on the wording that they use, because they keep using the chamber. So they keep using the reverberant chamber, diffuse, and at the same time they use the direct field acoustic test. So so things are evolving. So stay tuned. We are working very closely with these guys, and we are making sure that there is no misunderstandings. Because for us it's clear, everybody's clear, but then somebody read these and it's like, oh, Alex, but how? That's how it works. But we are working on these, and we can. The only things that matter is that we can satisfy the requirement in terms of overall level, in terms of tolerances, in terms of diffuseness. We can make we are all all compliant with this requirement. What I was telling you earlier, that it took us quite a while to be resolved as a question between RFAT, so reverberant field acoustic test, and DFAT. I think it's been solved not by us. I mean, we would be, of course, biased, but by aerospace engineers. So they took the same object, they put it in a chamber, they put it in a DFAT, and they did what we call it the back-to-back comparison. And they didn't look at the acoustic field as much, but they did look at the response. And so the response means that they took accelerometers, the same accelerometers, and they plotted one on top of each other. And they say, look at this. It's exactly the same. These work. So the vibrations are the same. And therefore, for us, this is a good test. So eventually, it took a few back-to-back comparisons, but we got there. Now, and when we talk of DFAT, there are, there's three things really that they make a DFAT system. There's a noise control system. You can see the SCADAs and the test lab there. There is a noise generation system, so the actual loudspeakers, amplifiers, and then there's the people that either run the test or design the speakers and design the controller. And this is a technology that requires, again, you don't learn it at school. There is none of you that went to school, nobody goes to school and learn how to do DFAT. No engineering school teach you that. They teach you some control, they teach you some structural dynamics, but this is nobody teaches control and loudspeakers and how to make a 145, 150 dB test during a spacecraft qualification. So you need to have a team that knows what they're doing. I'm going to leave the control part to Chris, and this is something that took from so not 3 days. You're not going to be here for 3 days. Don't worry, just going to be a few minutes. But Chris will give you that part. I'm going to give you some background about our team. I mean, is a team made of the best people in our industry. For you can see the average age is not the lowest, but that means that these guys have been doing this for a long time. We have people that Wes has been designing chambers for 30 years. Alan Medic has been testing satellites for 40 years. Marcus has been designing controllers for 50 years, and so it's a team of experts. And the other guys are. I was actually last night we went for dinner, and I went with the young guys. So these kids are in the 30s, and they're very young and they're very enthusiastic. And before doing that, they were doing concert. Now, I want you to for a second. So one of the guys actually was in television. Now, it came from a television studios. Think for a moment the pressure that these people is used to. I mean, you are in a television studio, you are live, breaking news, or there's an interview, political campaign, whatever there is, and the microphone doesn't work, or there is somebody talking too loud, or there is a mix of microphone. So these guys have to troubleshoot real time, but not with an object, but with millions of people watching. You are at a concert, you're doing Taylor Swift, you're doing Pink Floyd, and one of the instruments is not working, one of the speakers, and people have paid a lot of money, and they're not listening, or they're not hearing what the pressure on these guys is enormous. So these guys are all professional of audio engineering and make sure that every cable, every connector, every decibel is accounted for, and it is very important. So this is something that too often gets underestimated. So the acoustic system is what we do, because we do not in the sense we design. Actually, we design and we also manufacture. So in a DFAT setup, there is a loop. There is a control, like a closed loop. So there is a circle of speakers with the microphone within which there is a satellite. These microphones are fed back to the controller, then based on the reading of the microphone generates the drive. and sends out the drive to the MSI control rack, so the audio part, which then send it to the amplifiers, which then sends out to the. And so this is the control loop. Is the closed loop that we deal with. And there is two people always sitting next to each other. One is the sound engineer here, crossover filters, where to put amplifiers, low, sub, high, and the acoustic control guys, how many decibel, and the reference profile, and the two talk together and they work together. Now, we decided to go and build our system in a certain way because not because we liked it, just because the request and the evolution of the industry. The subwoofer is one part of it. So it's like two speakers cabinets that we have. The subwoofers at low frequency up to 200 hertz, so 25, 28 to 200 hertz. And then there is a high frequency, so low, mid, and high frequency, which is the cabinet called MP150. That goes between about 150 and 10 kilo. We use it to 10 kilohertz. Now, what is important is these overlap between the subwoofer and the three-way, so the top, because that is the frequency. If you look at pick any random launcher manual, whether it's SpaceX, Vega, Ariane 5, 6, the peak sound pressure level is always around 150 200 dB. That is where the peak of the curve is, and so that is where most of the power is required. And for that reason, we designed these boxes to have an overlap there, so we can put a lot of power. And we have reached 150 dB with these speakers. 150 dB is a lot of dB. It's very noisy. So that's why we decided, but there will be another reason we decided to do that way, because then we can split and we can bring only the necessary equipment. So if you have to do a low frequency test, we don't need to bring high frequency speakers, and the other way around. Or there are tests that we're doing here for military purposes or defense or aviation, where the requirement is to go from 1 kilohertz to 30 kilohertz. So there's no point of subwoofer. There's no need of bringing subwoofer. So we have high frequency speakers that do that, but no subwoofer. And then there is, of course, the amplifiers that come with it. So each speaker is powered by 1 or 2 amplifiers, depend on the speaker. These are super high power amplifiers, which are made by a commercial company, but they are made on demand for us. It is like you can buy these amplifiers, but you cannot buy the one that we use. These are specific amplifiers made to have our extreme demand in terms of current and power to the speakers. So how does it look like? These are rendering, but I'll show you some pictures. We can do fat, slim, short, tall, depending on the size. So a speaker, a DFAT system for loudspeakers changes in size and height depending on the object. So 6x6, we call it 6x6, 8x8 is the number of stacks of one type of speaker. So you have a subwoofer, top subwoofer. We can arrange them in different ways. Here's one alternating, here's like together. This is a 10 by 10, 13. And these are all tests. So these are all rendering of real tests. So there's, in fact, we actually went above that, and you will see in a second. I don't think is the time to talk about it. So this is an interesting part, because we had a spec, and if you look at, this is the Falcon 9, and if you look at the 100 hertz, 1800 hertz frequency, in a Falcon 9, so in the normal space application, we are 123, 124. We were requested to do 145. So we couldn't meet 145, 100 decibel. So 100 decibel is a lot of subwoofer. So that's the subwoofer we should remember. So it's not the high frequency, it's the subwoofer. under that is still considered in audio technology a subwoofer frequency. And so the only way we had to do it was to put 18. So the flexibility of having that is where I was telling you earlier. The reason why we did that way is because of experience, not because we liked it. So we had 18 subwoofer surrounding the article and 6 of the high frequency. So that is how we managed to get some near. No, we didn't even finish it, but we went to 151.4. We couldn't meet, but the customer was happy enough, and they're really happy for what we've done. Technology that is been evolving has allowed us to do a lot of things. So we can run a 2 hours test on a low level. For us, 140 dB is a low level. We can run 2 hours continuously. The speakers don't feel that much heat. So things have evolved greatly. That's an overall overview that we set up anywhere in loading bay, an integration facility, anywhere there is enough space, we can load up. There's a crane overhead. We can just do our setup and then leave it as a cleaner than when we arrive. The other test, these are the records, the world records. The Guinness World Record, 15 meters, 50 stack, so 50 feet tall stack. So there's like a lot of loudspeakers, and you can see the way of putting them together to keep them together, preventing from falling. This is to prevent. This is responding to earthquake requirement. So and especially in South America, these would be a big. I was in Peru in February. We were eating at the restaurant. At some point, the table started shaking. So South America is one of those places where you wanna make sure that there is a earthquake requirement applied to these very tall stacks. So yeah, we've been doing that. So this is for California. California is probably the same level of activity as South America. But yeah, this is things that we have been thinking and designing for. This is the hardest part, actually. When you have a test like this, the hardest part is not the acoustic part, but is the structural engineering to make sure that doesn't fall off and doesn't fall on the spacecraft. Some noise level that we made. So let me recap. And yeah, there is 3 parts, and we master all of them. We are ready to come and demonstrate, do it for you, test your satellite, noise control system, noise engine system, and our team are today the leading technology. We're still making. I mean, what we've been doing for the past 25 years is, of course, what you see today, but what we're making in the background is things that you will see soon. But things are changing and are evolving, of course, continuously. So we're going to leave you to talk, to discuss, to question. Now this is my book. I just put it there because it was I'm using slides from there. I will send these to Gabriel in academia, like an academic book. So I'll be happy to answer questions, or later to collect questions. Bradley can collect questions, and we can chat on some of the topics you are interested.
Perfect. Thank you so much, Alex, coming in. Chris, I think the floor is yours.
Brand. So
Awesome.
Brad asked me to come on and take a look at or present some of the controller capabilities. So yeah, I'm an application engineer with Siemens, and our little corner of the world is the controller portion of this. So some of this, I'm sure you're familiar with at this point. It's going over some of the same stuff that has already been presented, but you launch something into space, there's a lot of different loads that impact your test article, whatever you're launching. So in the user launch manual, there's shaker vibration test specifications, acoustic noise specifications, and shock specifications. The Siemens software can do shaker control and acoustic control. We cover the whole range of anything you might need to do on something you're launching. And of course, there's some real challenges here to doing satellite testing because you don't really get a second chance. When you launch something into space and it's broken when it gets there, you start all over again. Millions of dollars in space junk at that point. So it's really important to qualify everything. And again, in a spacecraft test, you might do some of these, you might do all of these. The Siemens Test Lab software covers all of these different test modes, but specifically we're talking about acoustic testing right now. Sure, we're all now familiar with the differences between RFAN and DFAN. But DFAN's a lot more convenient for a lot of reasons. And one of the best reasons is that a DFAN test itself is more controllable than a reverberant chamber. Reverberant chamber shoots sound out of the horns here, bounces around the room, and the room's going to do what the room's going to do. There's no controlling the sound field in precise locations in the same way that you can with the DFAN test. So again, RFAN, expensive. DFAN is a less expensive way to do this kind of testing. And yeah, you have a lot more flexibility with the DFAN test than you do with RFAN because it's a physical structure. Now, we say DFAN is a less mature technology just in terms of time, right? DFAN's been around for 20, 30 plus years. RFAN test has been around 60, 70 years, right? So we're not talking about something brand new here. It's a proven technology. It's just doesn't go back as far as RFAN, right? So important to understand that. Two major differences you see in data with RFAN versus DFAN is DFAN gives you better homogeneity for low frequency versus the reverberant chamber, right? So we've got much tighter control than you get with an RFAN test, especially in these low frequencies. But arguably, the low frequencies are the most damage, have the most damage potential on your spacecraft. And so those are the more important frequencies to get right and excite your structure. It's important to understand that the DFAN controller is a MIMO controller, right? As opposed to what we call SISO, where you have one drive and one control mic. With MIMO, you have multiple control locations and multiple drives that are going to all of these. So if you only have one drive to play with, it's not possible to control uniformity, right? Because you're putting the same signal out to every speaker. What the MIMO system is doing is varying the signal that goes out to each one of these speakers so that these microphone locations are going to give you a uniform field. And we can see this is a reverberant chamber. versus CISO or CIMO is in blue, and that's the worst correlation, but the MIMO control loops and the reverberant chamber responses on this reflector are pretty much the same. And that's really what we're looking for here, right? We want the response of our test article to be the same as the response it would see on the launch vehicle. Okay, again, main goal of DFAN is to get a uniform pressure field around the test article. You almost always have the same sound pressure level profile in all the points. There are some exceptions for that, and the Siemens controller can have what we call a spatial average of different microphones. So you can set different profiles for different microphones, but generally for DFAN, 99% of the time, you want the same profile in all measured locations. So again, back to this launch vehicle user manual. These are some acoustic profiles for different launch vehicles. They're in decibels over octave center frequencies. And this is how you program it into the controller. Okay. So I think Alex already went over some of that stuff. So let's go right into about MIMO control. There's a couple things that go on in the background that the controller just takes care of, right? With a MIMO control loop, we're not controlling like a reverberant chamber where you're just basically controlling octave bands. With a MIMO controller, we're actually in the background controlling to a narrow band random pressure PSD. And that has a lot of advantages because you can more finely tune the field, right? You can tune the field at a single frequency line with a PSD approach as opposed to an octave band approach, where you're just basically using equalizer sliders to change the energy level of the entire octave band, but an octave band can cover quite a broad frequency range. So instead of changing all the frequencies between 8 kilohertz and 10 kilohertz, we're just maybe changing a single frequency line to bring that into spec. I don't know, did anyone show a video of a setup yet?
No, not yet. This is awesome.
It's a DFAN test being set up. Lots of amplifiers there. Lots of speaker stacks. Spacecraft going into position there. And the ring's complete. There we go. Sending some noise out to the loudspeaker system. And so that was a qualification for this Thales satellite, the Cosmos SkyMed, and some results, right? Pretty accurate, right? And this is also kind of what we want to see, and one of the things that the controller focuses on is making sure that our average response doesn't go below the test specification. We kind of want to lean towards a little bit more than a little bit less, right? Under testing being more of a concern than over testing in space generally. And here was the specification level. It's 143 dB overall sound pressure level. And also note the tolerances, right? The tolerances are very, very tight for DFAN. Generally with vibration testing on shakers, we're looking at plus or minus 6 dB tolerances. All right, so it's a couple questions that you have to ask yourself before you get started here, and all these questions are answered in the controller, right? Target matrix is defined in terms of PSDs and CSDs. This target matrix, by the way, CSD, this is power spectral density and cross spectral density. And this target matrix is done in the background for DFAN, right? So you just tell the DFAN controller what you want the overall sound pressure level to be. And through some pre-test analysis, we figure out what this target spectral density matrix needs to be. That matrix then gets inverted, and sometimes you end up with non-square matrix math here, which gets kind of interesting. You might ask yourself, how do you invert a non-square matrix? Well, got singular value decomposition, which we'll talk about in a second here. So in general, what we're doing here is we want to figure out what the output is. We measure this frequency response function or transfer function in a pre-test step. And then to figure out what this drive needs to be in volts, you invert this transfer function and multiply that by your reference spectrum, and that gives you what your drive in volts needs to be. So with a single shaker system, this is pretty straightforward, right? Because you have one drive output and you have one average control channel that you're going to use for this. So it's basically doing an inversion of a single FFT or FRF, which is not complicated at all. But it gets real complicated with a MIMO system because you have multiple inputs and multiple outputs. So you have a whole transfer function matrix, and that gets tricky with inverting that. So you have to solve this system of equations. Now, this leaves us with this kind of issue here, right? We either have to have square or rectangular control, right? If you have more drives than control channels, you have an overdetermined system that you can't solve. But if you have less drives than control microphones, you have an infinite number of solutions to that matrix, right? So we do this pseudo inversion step and apply a least squares solution to try and get everything as close to the reference specification as possible. I know I'm going through this fast. It's just to kind of give you a flavor of how this works. I think I'm gonna skip ahead One of the features in the software, or one of the issues that you have with DFAN testing, is figuring out where you put microphones and which microphones to use for control. The Siemens software has an algorithm that looks at all the microphones that you set up and can pick a specified number of microphones for control. So basically you could set up 30, 40, 50, 60 microphones if you want, designate them all as potential control candidates, and then this optimization algorithm is applied and gives you a choice of different solutions to apply to get the best result that you can. There's some other interesting features in the software. You can take your measured data and right after a test, start to see how your test article is moving, right? So we can take this data right from a DFAN test and come up with operational mode shapes that give you a picture of how your test article is moving during the test. So that's my couple of minutes on DFAN testing in a nutshell.
Awesome, Chris. And just for clarification, I guess a question I had for the audience too is, you mentioned at the beginning a lot of tests outside of just acoustics. Can the same controller and software be used for other spacecraft tests or satellite tests?
Yes, exactly. So even within the same project file, I guess that's maybe something to pull up here. Go right into here. So this is the Siemens software installation, and what you end up with is access to all of these different options for test mode. So my little slice of heaven here is environmental testing. You have acoustic control. This is reverberant chamber control. MIMO random, which is where the DFAN lives. Is mission synthesis, which is not really part of this. That's basically taking field data and turning it into a test specification. Random control, MIMO shock, swept sign, waveform replication, and MIMO waveform replication, track sign dwell, transient capture for capturing shock applications. But MIMO random, it's pretty straightforward. So any one of these projects, any one of these test modes, you can actually open the same project in. So for instance, I was just doing a sign test yesterday. I'll just open this up. And the software flow is along the bottom here, right? So you can set up your test article geometry here, set up your different channels. So this would be where all the microphone sensitivities and stuff go. There's a calibration step here, which is optional, but this is where you would hook up your piston phone to each individual microphone, and you could do a calibration here. So you'd set that to like Pascals, for instance, doing microphones. Then you have your MIMO random setup, and we'd pick acoustic, spatial average. This is where you'd put in your reference spectrum. If I put a couple more control channels here. So here's where you pop in your different levels. I'm just, etc. I'm just going to do something dopey looking real quick. I know that looks dopey, but thank you for rep. So you'd set up your profile there, and then you'd go through this pre-test step, which sends a little excitation out and measures the system transfer function. And then over here in the pre-test analysis is where you'd run that optimization algorithm if you choose to do it. And then it's right into running control. You kind of got a flavor for that in the video, how that looks. Obviously, I don't have a defan system here, so it's kind of hard to actually show a test run, but that's kind of how the software flows and works.
Awesome.
Then any data that you want to display ends up in the navigator here, and just drag and drop data in. That's
Looks like
my nickel
Dr.
for the
Sanca.
software.
Dr. Sanca has a question.
Yes, thank you. It is really impressive. I was seeing the videos like bigger than a stadium. I put in the chat. It's really, really impressive. Maybe to Alex, the question, you are completely independent with the room. I mean, with the direct test, with the direct field acoustic test. I mean, the room is not important.
Well, that's I wouldn't say that's entirely true, right?
Okay.
There's issues if you get the speaker stack too close to the ceiling. You can have some reflections from the ceiling that create an uncontrollable situation.
Okay.
So room geometry where the speaker stacks are can be a factor, but generally, I think the guys from MSI can speak to that as well. But generally, no.
Okay.
If you have a large enough room, go ahead, Alex.
No, what you were saying is true. So you can have the only risk is you create a cavity. So if you have a ceiling that gets really close to the speakers, then you create a cavity, like a cylinder, which is so the controller will struggle a lot. But basically what the controller does is to beat the crap out of the physics of the room to flatten those modes. You always have modes in the room. You just the MIMO controller in narrowband trying to remove those peaks. And so that's why there is a lot of energy eaten by the control. So if you just have a set of speakers and you drive it open loop, you could reach 150 dB and measure a lot of pressure. But if you want a uniform field, that's where things change. Then the controllers start to eat a lot of power and then consume a lot of drives because you have to bring down and bring up those peaks, and where there are antinodes, then you have to bring up the level and try. So that is the controller work. If you test in an open space where there is a lot of vibration, then the controller will breeze through and everything will be a lot easier. So it is what Chris is correct. There is the room can help or can fight controller, but eventually the controller will win.
Great,
but
thank you.
Do the best you can.
Thank you.
Well, awesome, everybody. I know we're up on time here. In the last 60 seconds, I just wanted to thank everybody for attending here. In the bottom right, you can see our email, info@msidfat.com. If anybody has any questions, please feel free to send those to the email address, and we will follow up with you after the webinar today. Chris, thank you so much. Dr. Sanca, thank you so much. I think we all learned a lot about the capabilities of LabOSat for small satellite testing from MSI, about acoustic testing as an innovative approach that can help be a little bit more economical, and some of Siemens' solutions to do all of these different types of tests in just one platform. So thank you so much for your time today, everybody. I hope you enjoy the rest of your day.
So